Hi, this is Ryan Chatterson, and during this session, we're going to be covering equipment selection, sizing, and sourcing. Okay, so to start off, we're going to talk a little bit about radial flow settlers. Now, a radial flow settler is the preferred first stage of mechanical filtration in a recirculating aquaculture system, and it should be in a recirculating aquaponics system as well. These are commonly sized by the inlet flow rate. So if you're going to buy this off the shelf, you're going to buy a unit and it's going to tell you maximum flow rate 10 gallons per minute or 50 gallons per minute. And that's how you buy the filter, sized off of the flow rate coming from your fish tanks. WMT Technologies makes wonderful radial flow settlers if you're actually purchasing a filter. And there's a couple of links here provided where you can get some detailed specifications on their radial flow settlers and on the specifications of those units. Here's one of the tables from WMT, and just to give you an idea, it gives you the max flow rate right here in gallons per minute or liters per minute. And we can see as the settlers go up in size, we have 7.2, 11.8, 21, 28, all the way up to 600 gallons per minute, that's going to be a humongous filter. If we look over here, it tells you the height, tells you inlet, tells you outlet, a lot of other specifications here on what the diameters of the piping are. And you can see here, inlet 0.75 inches, and outlet 1 inch. They actually build a little larger outlet in here so they don't have any kind of head pressure leaving the outer collection chamber on a radial flow settler. And here's a great picture from WMT of their unit. And this is really what I think most aquaculture people are going to model their radial flow settlers after. This is the widely accepted design. And again here we've got our inlet. It comes in through the sidewall, and it does a 90-degree going vertical up. We've got the stilling well that goes over the outside of that pipe, a larger diameter pipe that actually dampens the velocity of the water and the particles. And as the water goes up and it reaches the surface, this outer stilling well actually goes above the surface of the water. So when the water in the inlet pipe comes up, it has to turn around and go down because it's not going to go over the rim of that pipe because, again, it's above the surface. So the water changes direction and goes down, and then it changes direction again as the velocity dampens again, and it goes back up. It falls over the sawtooth weir, and it actually goes out of the collection point. This is a cut in half, but you can see the exit pipe here is cut in half going out of the back of that filter. That's how they work. Here's the sludge collection. Again, your sludge is going to be in the bottom of that 45 to 60 degree cone. Open up a valve and it sucks it all out. Here's a picture looking straight down in the middle of one of their radial flow settlers. Now you don't see the outlet weir quite like we just saw in that picture before because it doesn't have a bottom on it. It drops down and collects the water down there. But you can still see inlet pipe in, changes direction, back out over the stilling well. Over the sawtooth weir. So, important design criteria for a radial flow settler. What's the engineering design specifics behind these things? Well, the actual tank should be close to a 1-to-1 ratio of height to width, not counting the conical bottom. So we've got a tank that goes down and then has a cone bottom. Well, not counting that cone bottom, we should have about a 1-to-1 height to width ratio there. Wider tanks equal slower velocities because, again, we can dampen that flow a lot by having a really wide tank as the water flows back up. But they require a deeper cone, a settling cone. So to get a 45-degree cone on a 30-inch wide tank is going to be a lot shallower in depth than if that was twice the width because the cone has to go really far down to actually, to meet, because the wider it is, the longer the cone's going to take to meet each other on each side. So again, wider tanks are better, but you require a much deeper cone for that. We want a minimum of a 45-degree slope on that cone, but a 60-degree would be preferred if you can fit that into the design. Unfortunately, when you're using large filters, That 60-degree slope is so tall that it makes it very difficult to install the filter a lot. It has to be dug in really deep or a really large stand. So most of the time you're going to see a 45-degree. That's what you see on most of these. I can tell you a 30-degree slope looks like you would have solids going out and settling down to that collection pipe, but when you open the valve, it will suck the center out of that sludge pile, and the other waste collected on the sides of that 30-degree cone will just sit there. So don't waste your time or your money designing one of these filters with an inadequate cone unless you know going into it you're going to have to get down there with a squeegee or with something to actually force the solids down into that collection pipe to be removed from the radial flow settler. 5-minute retention time, 3-minute minimum. That's really fast, I think, but I do see those people designing around that criteria. But I like 5 minutes retention time in that radial flow settler because following the other design criteria, that actually gives us the proper velocities to let the solids fall out. And something to point out, again, 5-minute retention time in these filters. In the University of Virgin Islands, they're going to be a lot larger, a lot longer retention time. I believe it was 20 minutes off the top of my head, but I believe that's right, 20-minute retention time through that clarifier. 5 minutes, 20 minutes. Well, right there you can see you can be a quarter the size of the vessel, which saves you a lot of money and it produces more solids, so it's much more efficient. We want a minimum of a 3-to-1 ratio for the vertical stilling well diameter, so that bigger pipe that comes out of the top. We want a minimum of a 3-to-1 ratio for that to the inlet pipe going into the tank. And a 4-to-1 ratio is even preferred. And what does that mean? It means if we have an inlet pipe, here we go, going in that's 2 inches, well, that stilling well is actually going to be 6 to 8 inches so that you actually have a dampening of velocity. The whole purpose of this filter is to slow those particles down in a staged effort to allow them to fall out of suspension. So the stilling well length here, it's going to be 80% of that tank's vertical wall height. Again, we talked about the vertical walls and then the cone. 80% of that vertical wall height is the length of that stilling well. We want a minimum of a 3-to-1 ratio for the tank diameter, okay, the entire tank for the radial flow settler to the stilling well diameter. So very similar. We jumped up here, 3-to-1 ratio, it slowed it down. Here, 3-to-1 ratio, it slows it down. And again, 4-to-1 is preferred. And we talk about preferred a lot here. Well, we can do all the calculations in the world, but when you go to purchase that tank, very rarely are you going to get the exact gallons that you came up with in the calculation. So we know what the number is going to tell us, and then we know what we prefer. So if we have to go either way, you want to lean towards, you know, a larger tank, a wider tank. And that's why I'm trying to give you these numbers and this insight into how you have to make these decisions. So minimum 3-to-1 ratio for the tank to the stilling well diameter. In this example here, if we have an 8-inch stilling well diameter, we want a minimum of 24-inch, but in the range of 24 to 32-inch wide tank, so the velocity is slow and the particles fall out. Do you see the trend here? Okay. You see how the filter works. It's not just a piece of equipment you buy. You see what the engineering and the design behind it was meant to do. We have a staged reduction of velocity, which allows those particles to settle. The 3-to-1, the secret to settling, we laugh a lot about this, but you know, this is the ratio that allows things to slow down in an aquaculture filter, and this is a really pertinent ratio to remember in a mechanical filter. If velocity equals 2 feet per second in a 2-inch inlet pipe, the water will slow down to 0.5 feet per second in that stilling well, and then it will slow further to 0.125 feet per second in an 18-inch diameter tank. So you can see we've drastically reduced the water flow in this vessel from 2 feet per second to 0.125 feet per second. That does a lot to allow heavy solid particles to fall out of suspension. So this center outlet radial flow settler, so I invented this, okay? This came out of the need for a radial flow settler and not having the ability to construct the sawtooth weir around the rim of a radial flow settler. Now there's a lot of ways that you can make a radial flow settler. You can have a single outlet on the side. We can do a lot of things, but many of those DIY fixes that you may see at other sites or online that come up, they disrupt the radial flow within that vessel, and it ruins a lot of the properties that are allowing these solids to settle. So I was trying to do something that would not disrupt the radial flow, allow the same speeds and same stage reduction of velocities, but make this something we can make at home if you aren't on a say a commercial size project, an industrial scale project where it's within the budget, you know, to buy that mechanical filter. Well, for everyone else getting into this, maybe that's make it or break it between buying a couple $1,000 filter and making one yourself for a few $100s. Well, that's who this is for. And I would not come out and say this is better than your off-the-shelf radial flow settler from WMT. Of course not. You know, they have the engineering behind it to make it exactly what they need. But this works very close to as good as that. The one downside would be that we have one more horizontal pipe in that tank. So it's another surface for solids to settle on. So that would be a downside. But the upside, which you'll see in a moment, is that we create larger particles from anything leaving this tank, which makes the next stage of filtration more efficient. So we have some pros and some cons, and we'll let you decide on this while we explain it a little bit. So this works using exactly the same principles as your standard radial flow settler with a sawtooth weir. The sawtooth weir is the one difficult piece to manufacture at home, like I just mentioned. Instead, we install a center outlet with a fitted plastic disc that reduces the velocity of the water traveling to the outlet. So this plate also acts as a settling plate, and it creates larger particles, increasing the efficiency of the second stage of your mechanical filtration. For center outlet radial flow settler designs, that top settling plate should be 75 to 85% of the diameter of your radial flow settler tank. Okay, and here's a picture of the top settling plate on that radial flow settler. And you can see as the velocities come over the edge, instead of coming up and going outwards over the sawtooth weir, they're coming up and they're going inwards over the settling plate. So exactly the same action in the filter, but it just takes a different direction at the top. And here, as it comes over the filter plate, is when it's traveling its slowest. So you see the particles settle out on this plate. And as it gets closer to this outlet, the velocity is speeding up and it's getting faster. And at this point, the velocity is so fast that solids are no longer settling on that plate. They're going to get sucked down the filter and move on to the second stage, to our K1 upflow filter. But it could be your drum screen filter or whatever the second stage filtration is. So we can see the reduction in velocity and then the increase in velocity as it makes its way towards this drain. Now what this does is, as small particles, really microfine particles, make their way, they bounce into other particles and they're attracted to each other, so they stick, they flocculate. And as those particles hit each other and form, they form larger particles, and they keep bouncing into each other until it is either time to clean the filter and we wipe them down and drain them out of the next stage of filtration, or they form a rather large particle. It goes through here and it actually settles out with a radial flow in the cone bottom of our next stage filtration. So it's made a larger particle and it allows it to settle out with the same type of methods. So this is great for secondary mechanical filtration. Oh, I'm sorry, we're hopping onto the K1 upflow filter now. So we'll talk about the K1 upflow filter. Now, we're building the center outlet radial flow settler. I believe it's later in week 4. So you don't have to worry about the rest of the specifics. We'll go over that in a lot more detail so that you know how to build them at home. Moving on to the K1 upflow filter. Now, this is great for secondary mechanical filtration, meaning after your radial flow filter. This is to capture finer solids, those solids that are left over that make it over that plate, the really fine solids. Well, this is to capture those. This is low head loss. It's not a pressurized filter, so you don't have several feet of head loss going through the filter. There's relatively zero head loss if you size the piping right. It's gravity driven, so we can flow right, from our tanks via gravity through the radial flow settler, then through the K1 upflow filter, all with gravity. No big head loss. It's also used to polish water after a biofilter. That's common use for this because the biofilter will slowly shed bacteria, and this will capture that bacteria within the media. It's very easy to clean. We can clean this using high-powered aeration, so air stones down in the bottom to dislodge the particles from the media, get everything moving. Then we remove those stones. The media floats and the solids will settle down to the bottom. We open up the filter drain and suck them out. So it's real easy to do that way. We can also use a shop vacuum in reverse, so it blows and blow air into there, stir it up, dislodging that waste, let it settle, open the drain valve and remove it. And we also get an additional benefit of nitrification happening because it's full of K1 media, and wherever we don't have an abundance of solids getting captured, we're going to have fixed film nitrification happening on that media. So we have additional nitrification that we're getting as an added benefit. Now here are some of the design specifications, and these were laid out to me and to everyone else that I know of by Rick Jones in 2010. This is actually in an unpublished master's thesis. Rick's a great guy, an engineer that actually works for Pentair Aquatic Ecosystems, and he taught me a lot when I was getting involved in aquaponics on a larger scale. So he introduced me to this filter, and it's worked wonders throughout my career in aquaponics. We'll talk a little bit about the specifications here. The aerial hydraulic loading rate is 5 gallons per minute per square foot of media. If you want to look at it, the volumetric hydraulic loading rate is 2.25 gallons per minute per cubic foot of media. So that's how I look at it. You add up how many cubic feet of media you need, and you've got 2.25 gallons per minute per cubic feet of media. So let's do a quick example. Let's do 4 times this. So what's that, 9? So if we had 9 gallons per minute going through a filter, we would want 4 cubic feet of media for that. Okay, and then we move on to retention time. 3 minutes. So we want a minimum of 3 minutes for the water to flow through all of that media and for the solids to fall out of suspension. And what does that do? That has to do with the particle velocity. Just like in our last radial flow settler, we're slowing those particles down and giving them time to settle out while the water is percolating up through the K1 media in the filter. The aerial feed loading, so how much solids this can actually capture in the filter. You look at 2 pounds per square foot, or you can look at it on the volumetric feed loading rate at 1 pound of food for every cubic feet. So again, we're at 9 gallons per minute in that little example that I just kind of spit out there. 9 gallons per minute, we're at 4 cubic feet of media. Well, for volumetric feed loading, 1 pound per cubic feet. So we could do 4 pounds of food per day going into that filter. That's what it's rated for. So right there is all your sizing specifics laid out by Rick Jones at the, I believe it was the La Paz Sturgeon facility. He did this on a large scale and really good numbers, great information. So here's a side picture of the K1 upflow filter that I've got installed here at Chatterson Farms. And you can see here, this is, doesn't tell you a whole lot from this picture, but the reason this is important is because the sun is shining in and you can see where the media is. It's from here up, and from here down is actually open tank. And I sized the media volume off of the feed rate that we have going into this every day. And what's happening is this is actually the inlet pipe right here. So the water's coming in and it's diffusing out and it's going down. So you get a radial flow action. This is a cone bottom tank. So the water diffuses down, it changes directions and comes back up, and it goes up through this bed of coldness media, small little plastic media that packs together very tightly. As it gets to the top, I actually have a center outlet that's a standpipe. So it's in the center of the tank, and it has a standpipe with a screen, and all the water overflows through that standpipe out to From here, we go to the biofilter, to the next stage, okay? So what that does is allows all the water to travel up through here and then collect, go down the center, and move to the next stage of filtration. In Rick Jones's original design that he laid out, I actually think I should modify the one here, and probably will, but they have a T at the top, and they have a PVC that goes the length of the tank, and they have slots in that. So you could also do holes with screen. But that's the same way that we put a plate on the radial flow settler. It actually slows the velocity down, so it's not all exiting out of a center point, and it slows it down and gets an even pull through that bed. So I'll make that modification in the future, but here, you guys can create a better filter than me. Point being, we're still doing the same thing. Now, here is the top view looking down on this Caldness K1 upflow filter. So we've got the inlet coming in the side. Now, I actually extended this pipe all the way through and put a valve on it. Now, on the inside here, again, we've got the water, we've got holes drilled, we've got screen around it, so the water can diffuse out, or the waste can diffuse out, but we don't have the coldness getting back into those pipes. But if for some reason you get really large solids in here and they don't want to make it past that screen, my worry was that they would just settle in this pipe and there would be no way to clean them. So I added a valve here, and maybe once a week we open that valve and it will suck anything settled in that pipe right out, just due to the head pressure in that coldness tank. So it's another valve, another few dollars on the build, but it was really worth it. And again, once a week you see a nice slug come right out of here. This is the bottom drain, okay? So there's a cone that goes down. We have PVC comes up and it meets this true union ball valve. Now, connected to each of these drain lines, we have a clear piece of PVC, and that's so that we can inspect when the solids are done. When I open this, you will get dark brown, almost black, concentrated slurry that's going to drain. Well, when you're done and you've evacuated all of that, it's going to run clear. That tells you to turn the valve back and close the valve. So it's a very easy way to inspect when you're done flushing the solids without having to look in your solids collection tank or somehow have a visual at the bottom of that cone. And again, it's on the same way over here. Now, why do we have a union at each side? That's so that we can undo this clear pipe and scrub out the middle, because you're going to get algae, bacteria, some other stuff that will, clog it up after months and months of use and make it to where it's kind of hard to see the solids going through there. So we undo the unions, we clean it out, and we put it back in. If we ever have to replace that piece of PVC, we don't have to cut anything. We just buy 2 new unions, glue them on, cut the same size piece of PVC, and put it back in there. Now, this pipe is actually nothing. The outlet goes out of the back. The middle, goes down, but for stability reasons on that pipe, because it's a round tank and we're using uniseals, I went ahead and ran the pipe all the way across and put a cap on this end. And it also allows me, if I ever needed to clean this out, we can unscrew this cap, scrub it out, and then screw it back in. But there's nothing going on in the front. In the back, the water goes out, down into the ground, and goes back to the biofilter to the next stage. And this last picture just shows you down from the top, down in the middle of that filter, and you can see all coldness here. This is actually black coldness, so it's made from it's a knockoff coldness, but it's the same stuff. So coldness media here, and then we've got our center outlet 3-inch pipe right there, but it's got a piece of screen over it so that the media, again, doesn't fall down the pipe. You got to keep it in the filter. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.